Hey everyone, so this is the third and final video for the thermal expansion uh, chapter. So these are the extra problems. So you can pause the video and we'll go over this one in a second. Alright, so for this question, what we're going to do, now they give us numbers in the beginning, but what I want to do is actually solve algebraically first, and that's going to give me my answer for A, which is then going to lead me into B once I get it by plugging and chugging. Now, the idea here is that we have the glass tube and the mercury inside, and they're both going to end up expanding. And we want to figure out first a formula that's going to relate the change of the length of the mercury in terms of what's given. So what I'm going to do is I'm using the volume expansion equation. I'm going to use this now. For the most part, the inside of the tube, we're almost going to look at it as a cross section, is essentially a circle, pi r squared, times the change in the length of the tube. So it's the whole area times length. That's a cylinder, and that's going to be equal to the change in the volume of the mercury minus a change in the volume of the glass. So what we can do is we can use this equation and plug that in for the mercury and the glass. Of course, both of them are going to have the same change in temperature, so I could just pull that out. And then we also know that for the most part, the original mercury and the bulb had the same volume. So what I can do is pull that out and move the pi r squared over, and I get this equation for the change in the length based off of the expansions of the mercury and the glass. And then what I can do, since they give me the diameter, I just replace the radius with half the diameter. And when I get this, so the 2 that was underneath the d got squared and got pulled up into the front. So this is the equation that they're looking for. And that's pretty much it. Then what we're going to do is actually plug the numbers in. So this is the difference in the mercury and the glass. And then these are all the other numbers that they give us. And we end up getting that the change in length is 6.87 centimeters. All right. Here's the next question. You can pause the video, work on it yourself. We'll go over it in a second. All right, so the first question says that they want to know what the volume of the air when it's at 1 atmosphere would be. So we have this tank, and they tell us that everything else is the same. We have the same temperature, we have the same number of moles since it's a closed system. So we're just going to use the ideal gas law, setting equal PV equals PV. And we're going to get an equation for the volume at 1 atmosphere. So when we plug the numbers in, we end up getting that the amount of volume that's pretty much in that tube is about equivalent to 2,000 liters. This is going to lead us into part B, where it says that a person's able to consume 2 liters of breath 12 times and breathes 12 times a minute. So we're going to use a rate to figure out how long it's going to last. So we could say is that the time that the air will last is equal to the total volume that's condensed inside the tank divided by the rate which the gas is taken out at. So this is the total volume, and it's being breathed in at a rate of 24 liters per minute. So using this, we end up getting that it's about 85 minutes, or pretty much about an hour and a half almost. Now part C tells us that we're going to go to some depth. We're going to have a different temperature, and they want to know how long will the tank last. Now what this is going to have us do is kind of go back to what we talked about in one of the previous topics with fluids, as we're going to need to know what is the new pressure of the system. So what I'm going to do is I'm using this equation to figure out what the pressure is at some depth. Of course, we are going to include the atmospheric pressure. And since temperature is also the one changing, we're going to include that into our calculations as well. So we're going to set PV over T equal to PV over T. So this is using these initial numbers, and then this is going to be at that 20-meter depth. So solving for V2, what we're going to do is take these numbers and plug them in. Now, because a lot of my numbers are in atmospheres, what I'm going to do is instead of converting all these two numbers into pascals, I'm actually going to do the opposite and take this number, which would give me pascals, and convert it into atmospheres. So that's what this part is here. I have to make sure that these are in Kelvin. This one definitely needs to make sure that it's in Kelvin. If you kept it in Celsius, it would not work. Then with that, what I can do is I get that the volume of the air is essentially about 660 liters. Using the same method that we did for part B, I just take this divided by 24 liters per minute, and I'm getting that the tank would last about 27 minutes. So in part B at atmospheric pressure, the tank was able to last for an hour and a half. Now it can barely last half an hour. So it essentially decreased by 2/3 of its initial value. All right, and this is the last one. I thought this was pretty interesting. So pause the video, you can work on this yourself, and we'll go over in a second. All right, so the way this works is we have two metals attached at the ends so that they're going to be forced to expand together. Now the thing is, steel and brass have two different expansions. So the brass is actually going to expand longer than the steel does, resulting in it bending in a little arc. And what we want to know is, well, what is that radius which to the middle of the two items? So what we're going to do is first we have to figure out what is the length that each one is going to expand on. So we're going to use this expansion equation for both the steel and the brass, and we end up getting this, that the steel expands by this amount and the brass expands by this amount. Now realistically, because of the fact that the expansion of both items are going to be very, very small compared to their initial values, I probably should have solved this fully in algebraic terms. However, due to the lack of space for this, it wasn't really that easy. So I use numbers at this point. But I would have recommended that you solved in algebraic terms so that you get a little bit more of a more accurate answer. All right. So what we're going to do is use this equation. So this is relating the angular radians with the radius and the arc. So what we have here is the ratio of the radius of the steel beam to the inner part of the steel beam over the length of that steel beam is equal to the ratio of the inner brass radius divided by the brass length. So moving it to the side, it doesn't matter which one we solve for, but for now I'm going to solve for the steel's radius. And then that pretty much means that for the brass radius, it would be plus T for the thickness. So I could plug that in here. From there, what I would do is I distribute the LS over LB to both terms so that I can bring the RS over here and then pull an RS out. So I kind of skipped that step. Like I said, didn't really have a whole lot of space. And I end up with this term. From here, I would just divide this over to here. And what I'd end up getting is this. If you don't see how I do that, an easy way of saying that is I multiply both terms by LB. So this becomes LB minus LS, and then this just becomes LS. So then I just take this divided by LB minus LS, and that's how I got that. So from here, I get that the steel beam is going to curve so that it has a radius of curvature of about this 360 centimeters. Since I want the radius to the about middle part of it, what I'm going to do is just add the thickness of it, and I end up getting 3.58 meters, or 358 centimeters. And that's about it. So if you have any questions, please let me know. Otherwise, I'll see you later.